The discovery of the nucleus. What would happen if you fired a bullet at a sheet of tissue paper? Well, what would happen is the bullet would go straight through the tissue paper. Now imagine if every so often when you fired a bullet at a piece of tissue paper, one of those bullets bounced straight back. That's the equivalent of what the physicist Ernest Rutherford saw when he was firing alpha particles at atoms. So remember, there are two types of charge, positive and negative. Like charges repel and opposite charges attract. Now an atom is made up of two parts. It's got positive charge in the middle, called a nucleus, and it's got negative charges moving around the nucleus, and those particles are called electrons. Most of the atom is empty space. So in between the electron and the nucleus, there's just empty space. Now this isn't what people thought atoms were like. It's what we know atoms are today because of Rutherford's experiments. But before Rutherford, people thought that the nucleus was what was called a plum pudding. So they modelled it a little bit like a pudding. So they thought that what you had was all of the positive charge of the atom spread out evenly. And then inside the positive charge, you had little bundles of negative charge. So it was like the electrons were stuck like raisins in a giant cake, where the cake was the positive charge. So the positive charge was spread out evenly, and there were tiny packets of negative charge. Now, it turned out that Thomson's model for the plum pudding was wrong. So his student Rutherford proved that the atom does not have positive charge spread out throughout it like a plum pudding. Now the way Rutherford proved this was that he got a thin sheet of gold, and then he fired positively charged alpha particles at it. So an alpha particle is 2 protons and 2 neutrons stuck together. So the overall charge of an alpha particle is +2. So he fired these fast-moving alpha particles at this thin sheet of gold. Now this is very much like firing a bullet at a piece of tissue paper. The alpha particle has a lot of kinetic energy, it's moving fast, and the piece of gold is thin. So what Rutherford expected was for the alpha particles to go straight through and punch through the gold foil and be detected on the other side. In order to detect where the alpha particles were, he surrounded the gold foil in a fluorescent screen, so that every time an alpha particle hit the screen, he would detect where the alpha particle had been and could work out the angle that it had travelled. So if Thomson was correct, you'd expect the alpha particles to go straight through the gold foil, a bit like firing the bullets at the tissue paper, because even though the gold foil has a net positive charge, and the alpha particles have a net positive charge, so they should repel, if the positive charge of the nucleus was spread evenly throughout the atoms, any given point would have a very small positive charge. So even though the two things would electrostatically repel, the momentum of the fast-moving alpha particle would be enough to carry it through and make it punch through the gold foil. Right. But that's not what Rutherford saw. Instead, when he fired these fast-moving alpha particles at the thin gold foil, he saw most of the particles go straight through, but every so often some of the particles bounced back. So we can see that in Thomson's model, what we'd expect to happen is all of the alpha particles go straight through, and we detect the vast majority of particles in a straight line from the alpha source to the screen. But Rutherford's model, which he proposed after he found his experiments, is that because the positive charge is all condensed in a tiny point at the centre of the atom called the nucleus, and the rest of the atom is empty space, most of the alpha particles go straight through or are very slightly deflected. But every so often, an alpha particle hits the nucleus dead on. Because the nucleus now has all of that positive charge condensed into a tiny point, if the alpha particle hits that, even though the alpha particle has a lot of momentum, the two charges are big enough that the electrostatic repulsion is enough to significantly deflect the alpha particle and make it bounce back. So, in Rutherford's experiment, the key points of this: some positive alpha particles bounce back. So these alpha particles must have been deflected by a positive part of the gold. The rest of the alpha particles passed through without hitting anything positive. So the nucleus must be small and the positive charge of the atom must not be spread out. It must be condensed in a small point, the nucleus, with the rest of the atom being empty space. Now, Rutherford's experiment was crucial for discovering that the nucleus was small and positively charged. We now know today that the nucleus isn't just made of protons, it also has other particles in it called neutrons, and neutrons don't have any charge, so they contribute to the mass of the atom but not to the charge. Neutrons were discovered by another physicist called Chadwick, who did a different type of experiment. So we can measure nuclear radius by using the Rutherford scattering experiment. So if we think that we fired an alpha particle and it deflects by 180 degrees, so we fire it at the atom, then it hits the nucleus and bounces straight back. Right? It won't actually hit the nucleus. Because the force that makes it repel is the electrostatic force, the fast moving alpha particle will get closer and closer and closer to the positively charged nucleus, but slowing down all the time, until the force of repulsion between the positive nucleus and the positive alpha particle makes the alpha particle stop and then reverse direction and be pushed away. So there's some distance r, which is the shortest distance between the alpha particle and the nucleus. The alpha particle never gets all the way to the nucleus, it gets stopped and then reversed just before it reaches there. So we can work out what that distance is, this shortest distance of approach to the nucleus, by considering the energy of the system. So as the alpha particle moves towards the nucleus, it's losing kinetic energy. So it started with some amount of kinetic energy, and then that kinetic energy is turned into electric potential energy. So we can imagine that the total kinetic energy lost is going to be the total electric potential energy gained. If we equate those two energies, then we can see that we have an expression for the kinetic energy of the particle of the charge of the nucleus times the charge of the alpha particle divided by 4 pi times the permittivity of free space times the distance between them. And that distance between them is going to be the distance of closest approach. That's when all of the kinetic energy has been turned into electric potential energy. So for example, what's the distance of closest approach for a gold nucleus, where the gold nucleus has an atomic number of 79, if the alpha particle had a kinetic energy of 5.5 mega electron volts? So we can equate our kinetic energy to our electric potential energy and rearrange to find r, the distance of closest approach. Now, the charge of the gold nucleus is going to be 79 times 1.6 times 10 to the minus 19 coulombs, and the charge of the alpha particle is going to be 2 times 1.6 times 10 to the minus 19 coulombs. The kinetic energy is going to be 5.5 mega electron volts, which you need times by 10 to the 6 because it's mega, and then times by 1.6 times 10 to the minus 19 to turn it into joules. If we plug our numbers in, then we get that our distance of closest approach is 6.6 times 10 to the minus 14 meters. So the distance of closest approach is inside the atom, but it's about 8 times the nuclear diameter away from the nucleus. So the alpha particle got inside the atom, but it didn't reach the nucleus. Now, we can use electrons to work out the properties of atoms via electron diffraction. We can use that to measure the size of the nucleus. Remember, electrons behave as waves. Electrons are a particle type called leptons, so they don't interact via the strong nuclear force, only the weak nuclear force and the electromagnetic force. The de Broglie wavelength of an electron is given by Planck's constant times the speed of light divided by the energy of the electron. So, the wavelengths have to be small because we need a high energy electron. Now, if we've got a thin sheet of metal foil and we fire a beam of electrons at it, the electrons will go through the metal foil and they will diffract, and they'll create a diffraction pattern of maxima and minima that we could detect on a screen. The first minimum of that diffraction pattern is going to be given by the equation. The sine of the angle from the straight through line to the minimum is going to be 1.22 times the de Broglie wavelength of the electrons divided by 2 times the radius of the nucleus. So theta is the scattering angle, which we can work out. So we can see that we'll get this diffraction pattern of the intensity like we'd get from a circular aperture, where we'll have a big peak of relative intensity going to minima with then to maxima on either side of intensity. Now, the nuclear radius of a typical atom is about 5 times 10 to the minus 11 meters, about half an angstrom, or 0.05 nanometers. So if we imagine a Ferris wheel as an atom, then a grain of rice at the centre of the Ferris wheel would be the size of the nucleus. The nucleus is so small because the strong nuclear force, which is the force that holds protons and neutrons together, only works at short distances. About 3.3 femtometers, the strong nuclear force falls to 0. Now, nucleons is the collective noun for any particle that's in the nucleus. So a nucleon is either a proton or a neutron. As more nucleons are added to the nucleus, it gets bigger. So whether we add protons or neutrons, the nuclear radius gets bigger as we add more particles to it. And we can plot the radius of the nucleus as a function of the mass number, the number of nucleons we've got, A. So as the number of nucleons increases, the radius increases, but it increases as A raised to the power 1/3. So the radius of the nucleus is a constant, R0, times the mass number, A, raised to the power 1/3, where R0 is a constant, which is equal to 1.4 femtometers. Now, nuclear density is the mass of a nucleus divided by the volume of a nucleus. So you can imagine a nucleus as a sphere. It's not, but we can model it as a sphere. So protons and neutrons have almost the same mass, 1.67 times 10 to the minus 27 kilograms. So for an atom with mass number A, the total mass is going to be the mass number times the mass of a proton. Now the volume of the nucleus is going to be 4/3 pi r cubed, where r is the radius of the nucleus. But we can substitute in our previous expression for the radius of a nucleus, r is r0, a to the 1/3, and then work out what the mass divided by the volume is. If we work through the algebra, we can see that the atomic number cancels out. So the density of a nucleus is independent of the mass number. It doesn't depend on the number of nucleons that we've got in an atom. So the density of a nucleus is 3 times the mass of a proton divided by 4 pi times r0 cubed, where remember r0 is just a constant, 1.41 femtometers. So the density is the same for every type of atom. It doesn't matter how many protons and neutrons we have, because as we add more protons and neutrons, the radius increases and the mass increases, but it keeps the density of the nucleus the same.